The purpose of this lab is to analyze differences between the motion of an observed object, a model in which only gravity acts on the object, and a model with both gravity and the drag force acting on the object. We will apply Newton's second law, which states that F net equals mass times acceleration to explain the motion of a 30-gram foam ball as it is dropped. Due to Newton's second law, since the gravitational force acts on the ball, it initially accelerates. Since drag force is proportional to velocity, at one point F net will equal 0, which according to Newton's first law means velocity is constant. This velocity is known as the terminal velocity. Now, let's watch the video of my brother dropping the ball. The origin of the system is at the ball's center of mass at t equals 0. The negative side of the y-axis points down, so the ball moves in the negative direction. Measurements were calibrated to the radius of the ball, which was 2.5 centimeters. We will assume, for the purpose of this model, that only the y-coordinate has a value, which is not true in real life because the ball can move backwards and back and forth. Now, let's look at our program. Ball.vel is set to 0, a vector with 3 coordinates equaling 0 because v initial is 0. Fnet is set to a vector with y component equaling negative 9.8 times ball.m, which is the force of gravity. After some experimenting with the drag force coefficient, I chose 0.38 as the coefficient here, because it produced the closest endpoint to the experimental value, as you will later see in the graphs. To model the drag force, I used 0.38 times a vector with component 0, the magnitude of the velocity squared, because remember we're talking about a drag force which is proportional to the square of the velocity, and so we're using the magnitude of the velocity squared since we can't square a vector, and 0. Next, we'll look at our graphs. Drag force has a significant effect on our experiment, which explains why the no-drag model is not similar to the others. See, here. The model with drag in the experiment are closer, but there's still a discrepancy which can be explained by human error in choosing the center of mass in tracker, and also using an incorrect drag force coefficient. Remember, I chose 0.38 just because of different experimenting. So we can see that the experiment on model with the drag force have the same starting and similar endpoints. See? Starting and endpoint. They also both reach a terminal velocity where there is no change in velocity because drag force equals force of gravity. To see whether terminal velocity changes with a different v initial, as the question asks, we'll use the last 2 points of our drag model to estimate terminal velocity. So I did that here, and we arrive at negative 0.87 meters per second. We'll plug that back into our model and run it. So here's our model. We'll plug negative 0.87, which was the terminal velocity of the model with the drag force, where velocity equals 0, and we'll see if the terminal velocity stays the same. So now let's run our program. You'll see that the graph is a straight line, meaning terminal velocity is still negative 0.87, and changing v initial does not change terminal velocity. So this is the end of my lab. I hope you enjoyed. We talked about why the drag force changes the continued acceleration because F net at one point equals 0, which means velocity is constant, which is why it's a straight line, and right here you can see the straight line. So that's the end of my lab.